Hello, welcome to 15-Minute Math. So today we're going to talk about the derivative. So the derivative is just a fancy way of saying slope. That's probably the key thing you can remember from this video is that when I say derivative, I'm really just meaning slope, but it's a special kind of slope. It's the slope of a function at a particular point, as opposed to our normal definition, which utilizes 2 points. And this is one of the driving questions that really started Newton, Leibniz into trying to develop calculus, because before those guys kind of developed their methods, there was really no way to find the rate of change of a function or a quantity at a particular point. You always needed 2 points, which was kind of a problem, because if, let's say I had a particle, maybe I'm thinking about a track runner or something. So I've got a track runner. That's my guy. That's my track runner. There he is. He's running. Let's say he's running a 100-meter dash. So here's our start. Here's our finish. Wait, no. One end. Finish. I'm not a speller, give me a break. Anyway, so that's a 100-meter dash, and let's say, for the sake of argument, this guy finishes in 10 seconds. 10.0, he's a quick track runner, and so he finishes in 10 seconds. So what was his average speed? Well, the average speed would obviously just be distance divided by the time that it took him to run that distance, so fairly easy math here, 100 over 10. This person was running, on average, 10 meters per second. Okay, not too hard. But the question is, how fast is he running right here? Because we've all seen a 100-meter dash. They start at the starting line, obviously at rest, and then they accelerate. So they continually get faster until, maybe the 40, 50 meter mark, somewhere in here. They're reaching their top speed, and then they're kind of just holding that top speed until they finish. The good ones. If you're not so strong a runner, maybe you start to taper off before you finish. But that speed's not constant. It's not like this guy was running 10 meters per second the entire race. He started off well below 10 meters per second, probably accelerated to over 10 meters per second. And actually, they definitely accelerated over 10 meters per second. And then, held on to that top speed for some period of time. But before the days of Newton and Leibniz, there was no way to know this person's speed at this exact moment in time. The best we were able to do is to kind of find average speeds, kind of like that. And there's a good reason for that. So let's ditch the physical context and let's just think about it from a pure math standpoint. And let's draw us a coordinate grid here. We'll draw us an example function. I don't know why my example functions are always cubics, but they seem to be that way. Let's say I wanted to know the rate of change of this curve right here, which is to say the slope, right? Slope is the same thing as rate of change. And we'll just call that point x. Well, let's first of all talk about how we would do it, before the days of Newton and Leibniz. We would just pick another point, kind of sort of close to that. We would draw in a secant line that connected those 2 points, kind of like that. And then just find the slope of that secant line, and the assumption is the slope of that secant line kind of sort of approximates the slope of the tangent line, which is to say the rate of change at that particular point. The idea is that these two slopes should be roughly the same, and if they're not that close, we could just pick a point closer and get a better approximation. But there was no way to get an exact value, and that just stems from the definition of slope. So let me mark this up just a little bit more. If that's, we'll call that one x1, so we'll call this one x2, and of course the y coordinates we'll just call y2 and y1. Well, let's find the slope of this secant line. Slope is the change in y over the change in x. which is y2 minus y1 over x2 minus x1. But if I want to find the slope at our particular point, that would mean x1 equals x2. Those are the same location if I'm at a particular point, and y1 equals y2. And so you can see why that's problematic from this expression. If I make those substitutions, I'm going to end up getting 0 over 0, which is an indeterminate form. We don't really, there's no good way to interpret that. I mean, that's not giving us a sensible answer. And so mathematicians, you know, before Newton and Leibniz's day were kind of stumped. They did not know how to handle this. And it wasn't until Newton, you know, decided to use some other methods that we were able to figure this out. And in fact, the methods they used were the methods of limits. So it was the idea of limits. That's how he got around this, because when we use limits, remember, we only really care about kind of the pattern that we see as we approach some value. We're not talking about literally letting x1 equal x2. Maybe we just let x1 approach x2, and then just look at the pattern that results, and then complete the pattern. So let's jump over to Desmos and really kind of make this a little more concrete. So I've got a very similar setup. I've just got an example function. I've got this secant line drawn in. We're going to try to find the rate of change, particularly at that black point. I don't want to do the average rate of change. I don't want to do the rate of change of the secant line. I want the actual slope right at that one particular point. And we're going to talk about how Newton decided to go about doing this. But I do want to note, before we do that, watch what happens here. I've got the slope of the secant line here, and I've got this f prime of a stands for the derivative of the function f at the point a, and I'm just calling this x equals 6. That's going to be our a right now. So as I drag these points closer and closer together, notice I do get my slopes converging. I mean, this idea that if I just pick a point closer, I get a better approximation, that was a good idea. It's just the problem arises if I put b equals 0. You can see Desmos does not like that. If there's literally 0 distance between the 2 points, algebraic methods fail. Okay. If there's some non-zero distance, we get a very good approximation. I don't want a very good approximation. I want an exact answer. So let's see how we can do that with limits. And then in a following video, we'll do some actual examples where we're crunching through numbers and working through problems. This is more of a theoretical kind of video. So before we get going, we need to introduce some notation. This point that we'd like to know, we'll call its x-coordinate x. And since this function is called f, then its y-coordinate is just f of x. And then here's what we're going to do. To get from x to our second point, we're just going to go some distance. And we're going to call that distance delta x, change in x. So then, let's see, what point? Maybe I can use green, but I don't, yeah, I guess I'll use this green here. So this new point here would just be x plus change in x, right? I start at 0, I go over a distance x, but then to get to this point, I'd have to go over a further distance that we're calling change in x, so the total is just x plus change in x. And by the same logic as calling this f of x, this y-coordinate would be f of x plus change in x. Okay? And normally when we talk about slope, when I say normally, I mean when we were younger, we would say, slope is y2 minus y1, x2 minus x1. I want to keep that in mind, and we kind of want to think about this as like point 1, and we'll think about this as point 2. So now what we want to do is we're just going to set up our slope formula. So slope, back in 7th grade or whenever you first started doing this, you would think about it this way. Well, what was point 2's y-coordinate? F of x plus delta x. What was point 1's y-coordinate? F of x. Now, we're going to do the x-coordinates. We have x plus delta x. That was point 2's x-coordinate. And just x was point 1's x-coordinate. And you do notice, hopefully, that we will get a simplification here. In fact, these guys cancel out. We're just left with delta x. Now, the unfortunate thing is all we've done is rewrite the slope formula. This doesn't get us any further to finding an exact answer. So to get an exact answer, what we want to do is we want to take this delta x and we want to see what happens when delta x goes to 0. Right? We want this distance to go to 0. And that's what we call the derivative. The derivative is that exact answer when delta x goes to 0. And so we could write this. And I'm going to write it in the notation of calculus. Typically we would write it with this prime. This f prime is what we say. So f prime of x is equal to the limit as delta x goes to 0 of that expression. F of x plus delta x minus f of x over delta x. If we can evaluate that limit, then we'll know the slope or the rate of change of this function at this particular point. So, by the way, you may say f prime of x, or you might say just the derivative of f. Two ways to interpret that symbol there. Just the derivative of f, or you could say f prime of x, whichever way. But that's my expression, so in our following video, we're just going to do some examples of how do I use this definition to get a sensible answer for actual polynomials like, well, that arrow's not very good, but you get the picture. Polynomials like you see there.